Okay, so we talked about in the Monty Hall problem, we saw that there were a number of cases that we had to consider, and we were interested in, given a certain condition or given a certain situation, how do those different cases affect the probabilities that we're interested in? Here, we're going to formalize that a bit more and generalize those ideas in what's called the law of cases and subcases. Okay, so what is that? So what we're going to do is let's suppose. So we have our usual setup. Our usual setup, what do I mean by that? Is that we have a probability distribution on some set of events. We have an event C that can be partitioned into subcases. Call them C1, C2, etc. What does partitioned mean? So we have to be clear about the meaning of the word partition. Okay. So that means, first of all, that the CIs, these subcases, are mutually exclusive. So they're non-overlapping, they're disjoint, they don't overlap. They only one can happen. At most one can happen, but that they are actually also exhaustive. So they're mutually exclusive and they are exhaustive, meaning that their union is actually equal to C. So they exhaust all of the possibilities in C. So there are two conditions for a partition, need to be mutually exclusive and exhaustive. Okay. And so what we can see then is if we were to calculate or sum up over all of the conditional probabilities of each individual subcase given C, they would add up to 1. So let's visualize this a bit. As usual, we have omega. We have C, which is our case, call it a case, and we partition C into subcases, call it C1, C2, C3. So we have 3 subcases in this situation. Okay. And what we're interested in asking now is we say, well, let's say we have another event, call it A. I guess it could be a rectangle, but wow, they really not let me get what I want here. There you go. So let's call this A. And what we're interested in is, suppose we know what we know what the conditional probabilities of CI given C are, of each of the subcases given C. How do we compute probability of A given C from the conditional probabilities of the subcases given C? How do we do this? Well, let's realize that once we condition on C, we become confined to this universe. So the probability of A given C, what it now boils down to is the realm of possibilities is restricted now to here, right? So really the only possible events that can happen are A intersect C1. So A and C1 could happen. A and C2 can happen. Or A and any CI can happen because they are disjoint. And these are disjoint because the CIs are disjoint. And furthermore, the union of A intersects CIs is equal to A intersects C, right? This blue region is A intersect C. Well, it's actually a mixture region. That color, purple. A intersects C can be gotten by the union of these disjoint non-overlapping intersections with each of the subcases. Okay. So in this case, then what does that tell us? Well, we have probability of A intersect A given C. What's the definition of that? Well, we know by definition it's probability of A intersects C divided by the probability of C. But A intersects C is a disjoint union of A intersects CIs, right? So it's a disjoint union of A intersects CI. So then the probability of A intersects C, let me not skip that step. Let's be pretty explicit about this. This can be written as the probability of the union of AI intersects C divided by probability of C. But they're disjoint. It's a disjoint union, so it's a sum of the probabilities. Over the probability of C. But now what is the probability of A intersects CI? Right? Remember, probability of A intersect CI. Well, what's the probability of A given CI? We can express as probability of A intersects CI divided by the probability of CI. Right? So then this gives us, by moving the denominator over, we can actually write probability of A intersects CI is equal to the probability of CI. Let me move this over here. Oh, no, we're good to put it. I'm gonna move it in a bit, but it's probably of A given probably of CI times probability of A given CI. Okay. All right. So let me shrink that up a little bit. Sneak that up there. So that's just a note. So we're going to substitute that. Oh, actually, I should put it down here where I'm going to use it. So I'm going to use that right here to show for each I, I'm going to write probability CI, probability of A given CI divided by probability of C. And then we can go even one step further by realizing that this is the sum of probability of CI given C, probability of A given CI. Why? Because CI is a subset of C, implies that probability of CI given C, well, that tells us what? That tells us CI intersect C is CI, right? Intersection of a subset with the bigger set is just a smaller set. So this is equal to probability of CI intersect C divided by the probability of C, which is the probability of CI divided by the probability of C, right? So just to color code this a little, it's this. We see this here, and that's where we get this. And to color code this, this comes from yeah, I would need to color code this. That's where those pieces come from. Okay. Okay, so that gives us what's called the law of cases. Okay. So this is the law of cases. How do we interpret this? The conditional. We interpret this as saying what? The conditional probability of A in case C is a weighted average of conditional probability of A in each subcase. Okay, so the subcases here are the CIs. And we weight those conditional probabilities by the weight probability of the subcases. And in the special case, when C is all of omega, we call this the law of cases. Sometimes it's called the law of cases. I call it the law of total probability. It's also sometimes called the law of total probability. And what does that mean? That means that the probability of A given C, that's probability of A given omega, that's just the probability of A. It's a weighted probability of A given each of the cases, CI, times the probability of CI, where CIs are a partition of omega. Okay, so that's the law of total probability, a very important, extremely important. Something that's used over and over and over again. And so definitely important to understand where this comes from, be able to use it. And we're going to have plenty of examples to illustrate how this comes into play throughout the course and in the coming sections.